Dear students, we will discuss today about carbocations. Carbocations. Previously, we used to call these as carbonium ions. So, this is under the part of reaction intermediates. As the term itself indicates, these are neither reactants nor products. These are the intermediate things. Carbocations, carbanions, carbon free radicals, carbenes, nitrines, benzene. One by one we'll discuss. Today's class is about carbocations. Carbocations are generally having three bonds and one vacant orbital. Because of the vacant orbital, they will be having plus charge. So because of the three bonds, they will be having, this is one bond, second bond, third bond. Each bond is made up of two electrons. So total number of electrons will be 6 electrons. As number of electrons are 6, again we can call this is electron deficient molecule. So carbocations are electron deficient. They are in need of electrons. So these you can call charged electrophiles. The meaning of electrophile is electron loving. Electro means electron, phile means loving. Electrophilic, electron loving groups. Electron loving groups means negative charge loving groups. Negative charge loving groups means negative loving will be generally positive one. So carbocations are having positive charge, so they are negative loving, that means electrophiles. So electrophiles are generally having positive charge, generally having. There are some neutral electrophiles also, we'll discuss about that later. So here we are discussing about carbocations. So how the carbocation is formed? Generally, it is because of a homolytic cleavage and heterolytic cleavage. Two types of cleavage are there. We'll go with that one. For example, this is a bond. Homolytic cleavage means this bond is turning into two equal. That means two carbon atoms with three and a free radical. So a homolytic fission gives us free radicals. This is homolytic fission, means a bond is equally dividing. That means each atom is getting its own electron. And another type is heterolytic fission. For example, this bond is completely shifted towards this one. In this case, the first atom with the three bonds will be having plus charge. This we are calling carbocation. The second atom with three bonds and a negative charge. So this part is became like carbanion. This part is became like carbocation. Carbocation is having three bonds and one plus charge. Carbanion is having three bonds and one minus charge. So this is carbanion part and this is carbocation part. Carbocation means there will be three bonds and one plus charge. So these are generally sp2 hybridized. When sp2 hybridization is there, the geometry is planar triangle. So how it will be? Trigonal planar, or you say planar triangle. See, 1, 2, 3. This is planar triangle. There will be a, okay. This is the vacant orbital. A vacant orbital, these three are bonds. For example, if you are taking methyl. So this is the vacant orbital. sp2 hybridization, planar triangle. Six valence electrons, all are paired, so this is again diamagnetic. sp2 hybridization, planar triangle, 6 valence electrons, diamagnetic is the basic line that you need to remember. Now we'll go with types of carbocations. Types. First one, CH3 plus. This is methyl carbocation. This methyl carbocation is called 1 degree carbocation because this carbon is a primary carbon. CH3, CH2 plus. Here the plus charge is on the carbon which is attached with only one other carbon atom. This is ethyl carbocation. Carbocation, simply I am writing CC. Ethyl carbocation. This is again a primary carbocation attached with only one other carbon atom. Then we will see this part. This is a secondary carbocation which we call isopropyl carbocation. It is a secondary carbocation because this carbon is attached with two other carbon atoms. So secondary carbocation. Example is isopropyl. Carbon, if it is having all three methyl groups, then if it is having a plus charge, this carbon is a tertiary carbon, and this particular example is called tertiary butyl carbocation. Tertiary butyl carbocation. Now, if you consider all this, this will be the stability order: tertiary, secondary, primary, and methyl. This is the stability order. Why tertiary is more stable? We'll have a look at tertiary again. This is plus charge 1, 2, 3. We are showing these are the methyl groups. What is the nature of methyl group? Methyl is slightly electron pushing group. These groups we call plus I groups. Positive inductive effect. Plus I groups these are called. So these methyls are this methyl, and this methyl. You can take ethyl, propyl, anything, everything is okay. But they must be alkyl groups. These are electron pushing groups. They are throwing electrons, or they are pushing electrons toward this carbon which is having plus charge. This plus charge is indicating this is electron deficient. Electron deficient means it is in need of electrons. So when it is in need of electrons, these groups are supporting. If you take simple methyl carbocation, hydrogen is there. Hydrogen neither plus I group nor minus I group. So this is not going to support any type of electrons towards this kind of thing is not possible. We can't show like this. So hydrogen neither plus I nor minus I. So this is not getting any kind of stability because of these three hydrogens. That's why the stability order is tertiary, secondary, primary. If any methyl carbocation you are discussing, this will be the least possible. This is one type. So what you can say, stability of carbocations directly proportional to plus I groups. What are the plus I groups? Any alkyl group you take, any alkyl group, all alkyl groups are plus I groups. And stability is proportional to 1 by minus I groups. Except alkyl groups, remaining all groups you can consider as minus I. Definitely you can consider all minus I groups are they are causing less stability for this. Let's go with one example. For example, we are having CH2 plus and one NO2 group. NO2 group will be like this. Here oxygen is attached with nitrogen by a double bond. So this oxygen is accepting the electron pair like this. When electron pair is going like this, nitrogen will be getting plus charge. So this structure will become CH2 plus a bond nitrogen, a dative bond oxygen, a single bond oxygen, double bond was there, it is shifted here. So this is minus charge, this is plus charge. You can see two positive charges side by side. This is highly unstable structure. That means because of this NO2 group, this is getting less stability, or it is not getting any help from this group. So this will become least stable. So finally you can say plus I groups increases stability, minus I groups decreases stability. If you want stability of carbocation, there should be plus I groups, not minus I groups. We'll go with few more lines. Look at this one. CH2 double bond CH plus. This is called a vinyl carbocation, not stable. This is not stable. Okay. don't consider this one. This is not stable because the plus charge is present on the carbon which is having a double bond. Double bond carbon means more electronegative carbon. On more electronegative carbon, plus charge is not at all possible. So have a look at this reaction. CH2 double bond CHCl to give CH2 double bond CH plus and Cl minus. Whether this reaction is possible or not, if anyone asks, you have to say this reaction is not possible. Why? Because in this reaction we are getting vinyl carbocation. This vinyl carbocation itself is unstable. When it is unstable, the reaction never possible. So logic is very simple. If the intermediate is stable, then the reaction possible. If the intermediate is unstable, then the reaction won't take place. Just have a look at this one. CH3, C, CH3, CH3 trimethyl group, Cl. If it undergoes cleavage, what happens? Chlorine is out. So how it becomes? CH3, CH3, CH3 plus charge. Is it stable? Because of inductive effect, because of inductive effect, inductive effect, it is highly stable. That means this reaction is possible and it can convert into a tertiary carbocation. In this way you have to think. So finally we came to one conclusion: vinylic carbocation is not stable. Consider this and remove it from your list. We'll go with one more. CH2 double bond CH CH2 plus. This is called allylic carbocation. Allylic carbocation. It is stable because this electron pair can come here. This will be resonance. I am giving you again. You see CH2 double bond CH CH2 plus. Now the plus charge is on sp3 carbon. This electron pair is shifting here. So two sides are I am showing resonance structure. CH2 CH. This will become double bond because of the shift of the electrons. This bond shifted here. So this carbon is losing electrons. So it is getting plus charge. Both are almost similar structures. Electron pair shifting taking place and there you are getting plus charge. This plus charge is now on this carbon. So overall, when electron shifting takes place, because of the electron shifting, the system loses energy, the overall energy of the system decreases and stability will be increasing. So allyl is carbocation, tick mark. Allyl is possible. We'll go with one more. Look at this. This is CH2 plus benzylic carbocation. Possible. You understood the reason. This is the reason. That means resonance is possible. So how the resonance structure is? One structure I will show you. The remaining you can easily understand. For example, if this is CH2 plus, this electron pair will come here. So because of this, how the structure will be? These two bonds I am not disturbing. This bond has shifted here, so this will become CH2. There will be plus charge on this one. Then after this you can expect from this, after that you can expect from this. So total, as 3 pi bonds are there, it will give you 3 structures plus 1 original structure. So total number of structures will be 4 structures are possible. So in benzylic carbocation, the number of structures are 4 and more the number of structures, more structures, more stable. Simple line you remember. More structure, more stable. So the resonance structure should be more in number, then the stability will be more. Have a look at this. This is pi symbol. It is nothing but pH symbol. It is nothing but C6H5 symbol. This is nothing but a phenyl symbol. So this symbol, some books they mention like this are pH or C6H5 or the benzene ring. All the meaning is same. So have a look at this. pH CH2, pH 2CH, pH 3C plus, which is more stable. Here you see one phenyl group is there, so total number of possible structures will be 4. One original structure plus because of phenyl group 3. Here one original structure because of each phenyl 3, so total number of resonance structures will be 7. In this case 3 phenyl groups are there, 3 into 3 9 plus one original structure, so number of structures will be 10. More the number of structures, more will be the stability. So this is the stability order. Triphenyl carbocation is more stable than diphenyl than one phenyl. Okay, na? So benzyl carbocation, this is diphenyl and this is triphenyl. More the number of phenyl groups, more will be the stability. Remember this point. One other line will take. This is one very interesting point. Now aromatic. Aromatic carbon ions. How the aromatic carbon ions will be there? One simple example I want to give you. Look at this. 1, 2, 3, 1 plus charge. This is C7H7 plus. Have a look at this again. This is called tropylium carbocation. One special name for this, tropylium carbocation. How it is? 1, 2, 3, 4, 7-member ring with 3 pi bonds and 1 plus charge. 3 pi bonds means the number of electrons are 6, so it is following Huckel's rule. So it is aromatic in nature because of Huckel's rule. The next condition will see conjugation, double bond, single bond, double bond, single bond, double bond, single bond, charge, single bond. That means the alternative double bond condition, that is conjugation condition, is satisfied. Number of 6 electrons, that is Huckel's 4n plus 2 number of rule is also followed. Because of these reasons, this compound is going to be aromatic. The aromatic nature is because of the plus charge, so this is one stable carbocation, tropylium carbocation, aromatic and stable. One very special condition is there. This is a cyclopropyl methyl carbocation, highly stable. The reason is between the bent orbitals of cyclopropyl group and the vacant p orbital of this carbon plus charge group, bent orbital from here, carbon's vacant p orbital, there will be conjugation. I can't show here this conjugation on this table, but you can just understand this one. Because of the bent orbital of cyclopropyl group and the vacant p orbital of this one, there is a cross conjugation type. Because of this conjugation, this is going to be highly stable. So if we are having more than one group of this CH2 plus, if we have two groups CH plus and this one, and by chance if we are having one more here, so this is obviously having one group here, two groups are there, three groups are there, this is highly stable, this is second stable, this is third stable. So these points we have to understand. Now let's come to the final conclusion, that is overall stability order. The highest one is 3 cyclopropyls. This is the most stable one. After this, 2 cyclopropyls. Different books will be giving somewhat change in order, but you just follow with this one. This is most trusted one, CH2 plus. So 3 phenyl, 3 cyclopropyls, 2 cyclopropyls, 1 cyclopropyl, then tropylium carbocation, an aromatic one. I think you remember 7-member ring. After this we have a triphenyl PH3P, excuse me, 1 second, PH3, 3 phenyl groups, 1 plus charge. After this PH2CH plus. After this PHCH2 plus. This is almost equal to allylic one. You know how to write allylic? CH2 double bond CH2 plus. This is almost equal to a tertiary one. Tertiary carbocation almost equal to allylic, almost equal to benzylic. They are almost equal. After this tertiary, secondary after that primary after that methyl carbocation, and finally after this, if you have any vinylic will go to the last one. Least stable is vinylic. Vinylic is the least stable one. So this is all about carbocations. So final one line about carbocations is electron deficient. Number of electrons are 6. So because of 6 valence electrons, they are in need of electrons and they participate in reactions. And The stability order is cyclopropyls are better than tropylium carbocation, then phenyl groups attached to carbocation, after that allylic, after that tertiary, secondary, primary, after that we'll be having phenylic carbocation. Okay, this is all about carbocations. We will discuss about more other topics in next class. Have a wonderful time. Good day.